Okay, we'll go through the quiz key here. 1. Will precipitation occur when one drop of 0.10 molar silver nitrate is mixed with 1.5 liters of 0.0013 molar sulfate? And so this is going to be a QSP problem. And so we'll need to know what KSP is. And so we'll have to look up the KSP value for silver sulfate. So looking it up, silver sulfate is here, Ag2SO4. So 1.4 times 10 to the minus 5 is the KSP. I'll write that here. KSP 1.4 times 10 to the minus 5. And we'll have to check to see. The KSP equation is just going to be the Ag2SO4 solid goes to 2Ag plus SO4 2 minus. So the first thing we'll have to do is stepwise solution dilution. So one drop is going to be, we're going to assume is 0.05 milliliters. And so the silver ion concentration here should be 0.05. Silver nitrate's a strong electrolyte over, that's how many milliliters. This is 1500 milliliters here, 1.5 liters. 1500. So it's a 0.05 over 1500 dilution of 0.10 molar. And so what does that come out to? 0.05 divided by 1500 times 0.1. That comes out to 3.33 times 10 to the minus 6 molar. Now, the other one is really a negligible dilution, the sulfate that is. The sulfate is going to be a 1500. Oops, this is 1505. I really doubt that's going to change it much, but let's go ahead and calculate. It's 0.05 divided by 1500. 0.05 times 0.1. It's the same. 3.33 times 10 to the minus 6. This is going to be a 1500 over 1500 0.05 dilution. It's minimal of 0.0013 molar. Let's see what that comes out to. So it's not going to. In fact, since this isn't a test on multiple choice, it's likely not to make any significant difference. Probably would skip this solution, but anyway, I'll just do it. And so it comes out to 0.010129999, which is a minimal dilution, but we'll do it nonetheless. All right, so when we're looking at QSP, QSP is going to be the silver ion concentration squared times the sulfate concentration. And so we'll just plug that in. Here's the silver ion concentration. So I'm not going to rewrite it. 3.33 times 10 to the minus 6. I could add more digits there to lower round off error, but usually for multiple choice, there's usually enough buffer there to compensate rounding errors. Times 0.0012999. I carried extra digits there, just right on 0.3. Anyway, here we didn't have to be so precise because if we look at the order of magnitude, 1.44 times 10 to the minus 14. 10 to the minus 14 is way less than 10 to the minus 5. And so QSP is much smaller, so no precipitation. What we need is a QSP greater than KSP, and we'll get precipitation. But it was significantly lower here. Okay, we'll go on to the next one. At what pH will 0.1 molar aluminum hydroxide precipitate? So at what pH will it precipitate? Well, here we need the QSP to be greater than KSP. In other words, let's take a look at the KSP for aluminum hydroxide here. And you'll be given a KSP table. We'll figure it out. And so we'll take a look up here. 1.3 times 10 to the minus 3 is the KSP. 1.3 times 10 to the minus 33. This is very small. All right, the KSP is going to equal, okay, well, we have the KSP equation here. It's aluminum hydroxide, solid, goes to aluminum 3 plus the 3 hydroxides. So we will need then the KSP is going to equal the aluminum concentration times the hydroxide ion concentration cubed. So to get the hydroxide equal to the KSP, QSP equal, in that case, the hydroxide has to be equal to the KSP divided by the aluminum concentration, and we got it to cube root 1/3. All right, so we know what the KSP is. Oh, actually, we want it to be greater than this. If I get this hydroxide, then it just equals KSP. So the hydroxide needs to be greater than that. But this is at the limit. And so we'll just calculate this. So just plugging in the numbers here. So the KSP is 1.3 times 10 to the minus 33. 1.3 times 10 to the minus 33. Divided by the aluminum concentration, which is 0.1, equals, and then I'm just going to do the cube root. So I'll just do this to the 1/3 power. That's going to give me 2.35. That's 10 to the minus 11. So if we get this hydroxide, then QSP would equal KSP. It would be just the right amount of hydroxide. But what we need to do is we need to get more than this. And so we need greater than this. Okay, and so, well, that's a hydroxide. Let's calculate the pOH of this. So we'll go on over here. Just ran out of room there. This is going to be very small writing because I have this blown up. So the pH is the negative log of the hydroxide concentration. So I'll take the log of my answer equals 10.62. 8, which gives me a pH of 3.37. And so this one, we need more. Or we could just say, the pH is above 3.37, which is going to give you more hydroxide. and we'll see it precipitate. And so this is the pH that's required for precipitation. At what this should have been at what minimum pH, because all these are going to have more hydroxide than required. And so at what pH will it begin to precipitate? 3.4. And it will continue precipitating out through 6.9 as we increase the hydroxide common ion effect, 7.1, 11.1. So at what minimum pH? Because that's going to give you the least amount of hydroxide. Silver ion salts are most soluble in water, excess sodium cyanide, excess sodium thiosulfate, excess ammonia, excess sodium EDTA. So let's take a look at these are all going to complex it. The cyanide ions will attack silver ions. And so what we're looking at here is we're looking at silver chloride. We're doing just a Le Chatelier shift. Silver ions plus, well, actually this is not silver chloride. This is just silver ions. Specific. And so what we want to do is we want to remove silver ions by complexing it. And so these are KFs. If we remove silver ions by complexing it, let's see what the KFs are. And so if we're looking at complexing silver ions, here, cyanide is 10 to the 18th, EDTA is 10 to the 7th, ethylene diamine was in choice, ammonia 10 to the 7th, thiocyanate 10 to the 10th, thiosulfate 10 to the 13th. And so it looks like cyanide is going to be the best at removing silver ions. It's at 10 to the 18 KF. So it's going to be cyanide. If we take two cyanides, and then we can form the dicyano or dicyanido, either argentate 1 ion. This is negative. Silver chloride should be more soluble in water, sodium chloride, sodium nitrate. Actually, this one I didn't talk about because this one I was going to talk about in lab. But this one is called the uncommon ion effect. And this is the common ion effect. And so it's going to be the least soluble in this one. And so it boils down to, is it more soluble in water or sodium nitrate? It turns out sodium nitrate doesn't participate in the KSP equilibrium. If we look at the KSP equilibrium, the silver chloride, solid, this goes to silver ions plus chloride. What happens, though, in the uncommon ion effect is this. The uncommon ion effect decreases the free silver ion concentration by forming these clusters. That is, what happens is the nitrates like to cluster around the silver ions. Depends on the concentration. You have a lot of nitrate in there, you get a lot of this clustering effect. And so essentially what it's doing is it's removing the free silver ion. That is, it's inhibiting free silver ion from reacting with chloride, basically. And so this is uncommon. This is not a stable complex like the KFs. We don't have a KF value for this. And then unlike the previous example where we formed these stable complexes. And the same thing happens with chloride. When we have the chloride, the free chloride concentration is diminished by having this clustering effect. And this is more prevalent at higher concentrations. And so some of the silver ions and the chloride ions will be clustered like this, which means that the actual free concentration is freely available to react here, silver ions and chloride ions, to precipitate out silver chloride. And so this one is a Le Chatelier's principle, just like the previous one, where we remove silver ions here, such that we're moving them, but not as effectively. And so this is a minor effect, it's a minor increase in solubility. And so there's a graph in the book. If we're looking at chloride here, we see that the solubility decreases dramatically with increasing chloride. Now the pen, increasing chloride. However, with the sodium nitrate, it's a very minor effect. That is, just a slight increase in solubility, or actually not increase. Increase, sorry, that's correct. A slight increase. This is going up. This is the solubility here. This is the concentration with increasing sodium nitrate. And so this is the common ion effect, decreases solubility. This is precipitation. That's what we get. However, the sodium nitrate would actually slightly increase it. 5. I wish to dissolve a solid containing silver chloride. A solution containing a high concentration of H3O plus should do it. In this case here, we're looking at saying if we could see a shift, Le Chatelier's shift to the right. Although this is a base, this is too weak. Because if I add H plus here, I'm going to get HCl. This is a strong acid. It's not going to do anything. So HCl doesn't even, HCl molecules don't exist. So it's not really going to remove this. And so I wish to dissolve it. I mean, having hydronium there will help it a little bit with the uncommon ion effect primarily, but not really attacking the chloride here in the Le Chatelier's. We need a bigger shift here to dissolve it. What is the percent precipitation of silver sulfate when 2 molar silver ion solution is mixed with 1 molar sulfate? What is the percent when 2 molar is mixed with 1 molar sulfate? This problem is poorly worded because is mixed. So there are two ways I could have handled this. I could say when. Well, actually, now I see why this problem is so big. Because we need something like this when equal volumes. If I said equal volumes, then what that is a 1-to-2 dilution, because I have 1 part of silver going to 2 parts total, and 1 part of sulfate going to 2 parts total. So it would be 1 molar and half a molar. Or I could say when we have a solution that contains both 2 molar and 1 molar, there's no solution dilution. The solution already contains that. But this is a very qualitative problem because some people will say 100% because I have just the right amount. I have 2 molar silver and 1 molar. It's a 2-to-1 ratio. 2 silvers and 1 sulfate. And so, but it's not. It's going to be less than 100% because of that. So let's say we're trying to precipitate out the silver ion. So if we look at the silver ion concentration here, and we increase the sulfate ion concentration here, what we're going to see is something like this, where it would take an infinite amount of sulfate to completely precipitate out. And so this requires an infinite amount of sulfate because here, when we're looking at the KSP equation, when we're looking at the KSP equation here, it's going to 2 silvers and a sulfate. And KSP is equal to the silver ion concentration squared times the sulfate concentration. And so in order to get the silver ion concentration to go to 0, that is, we have none left, the sulfate has to be infinite. And so it's not possible. 7. What is the solubility of calcium phosphate in water? Okay, this is just a standard ice calculation. And so if we do calcium phosphate, maybe I should do this on scratch. Running out of room here, but I'll just fit it in here anyway. So calcium phosphate, that's going to give us calcium, 2 of these, or 3 of these, actually 3 calciums plus 2 phosphates. And so if I just set up the ice table here, and then start off with 0 and 0, this is going to be plus 3s plus 2s. And so I'm going to get 3s, and then I'm going to get 2s here. And so the KSP is going to equal the calcium concentration cubed. So that's going to be 3s, so that's the calcium concentration equilibrium cubed, times the phosphate concentration at equilibrium. Phosphate concentration at equilibrium is 2s squared. So it's 3, 2, yeah. And so this is 3 cubed is 3 times 3 is 9 times 3 is 27 s cubed. And then this is going to be 4s squared. So that's going to give us, again, I'm going to have to go out this way. 4 times 27 is going to be 108. S to the 5th. And that means S is going to equal KSP divided by 108 to the 1/5. So we need the KSP value for calcium phosphate, which we can look up in the chart. So calcium phosphate. Here, 2.0 times 10 to the minus 29. 2.0 times 10 to the minus 29. That's my fault. Having a technical issue here. Let's see if that fixes it. Yeah. Let me just check that. 2.0 times 10 minus 29. Yeah. All right, so I'm going to just plug it in there. So 2 times 10 minus 29 divided by 108 equals, and then I'll take the 5th root to the 1/5 power. So 1 divided by 5 power. 7.137. Oops, not that one. This one over here. 7.13 times 10 to the minus 7 molar. Okay, so that would be 8 here. Okay, the least soluble solid is silver carbonate or silver bromide. These ionize differently, and so we can't compare the KSP. We actually have to calculate the solubility to be safe on these, unless there's a huge, huge difference in KSP. But let's take a look at the KSP values for each of these here, silver carbonate and silver bromide. So we go to the table here, and we take a look at silver carbonate and silver bromide. Silver bromide's 5 times 10 to the minus 13 and 8.5 times 10 to the minus 12. Okay, so these are the KSPs here, but the solubilities are going to be different depending on how they split. So this one's going to give us 2s if we do the ice table, you know. So for example, silver carbonate here, solid, goes to 2 silvers plus a carbonate. And so we assume 0 at the beginning, and then this is plus 2s, this is plus s. So we're going to have 2s and s at equilibrium. And so the KSP here is going to be 2s, the concentration of silver, and then we have to square that because of the 2 here. So that's going to give us 2s squared. And then carbonate's just s raised to the first power because it's 1. So this is going to give us 4s cubed. It's a relationship here. For silver bromide, that just splits up into 1 silver and 1 bromide. And so this is going to be we start off with 0 here. This is plus s, and we're going to get ss. So that's the silver ion concentration times bromide concentration, which is just going to be s squared. So we can figure out what S is for silver carbonate first. S is going to equal KSP divided by 4 square root. No, cube root. This is 3 here. So KSP divided by 4 cube root. And so that's going to be 8.5 times 10 to the negative 12 divided by 4 equals, and then we're going to take the cube root of that, so 1/3 power. I'll raise it 2, and I get 1.28 times 10 to the minus 4 molar. And then over here, we'll just take the square root of this. So S is equal to the square root of 5 times 10 to the negative 13. .07 times 10 to the negative 7 molar. So when we look at this is higher, 10 to the negative 7 molar versus 10 to the minus 4 molar. Actually, no, this is higher. This is a higher solubility. Although the silver bromide had a bigger KSP, so you expect it to be more soluble, it turned out the silver carbonate with a smaller KSP is more soluble because assuming I did the calculation correctly, you guys can check it. And so we can't rely just on KSP because we see the KSP of silver bromide is greater, but the solubility of silver carbonate, and usually if the KSP is greater the KSP, the higher the solubility. 9. All multiple equilibria can be solved using the simultaneous method. That's true. In fact, we're supposed to solve all multiple equilibria using the simultaneous method. It's just too difficult. And therefore, since it's too difficult, we try to assume stepwise works, the combined method, etc. but they're supposed to be solved using simultaneous method. 10. The combined method for solving multiple equilibria can be used for Ka1, Ka2, and Ka3. We can't combine these because the combined method only works when the first K is very large and the second K is very small. Oh no, I have it backwards. The combined method only works when the first K is very small and the second K is very large. But these Ks fall in succession. So this one's like 10 to the minus 3, 10 to the minus 5, 10 to the minus something. In fact, we could take a look at that. In fact, this was an example I did in class. So remember those. 10 to the minus 3, actually 10 to the minus 3, 10 to the minus 8, 10 to the minus 13. We can't combine these because we'd lose critical species. You can take a look at the notes, but I'm not going to redo it. It's false. Which is expected to be the most soluble in acid? Well, the most soluble in acid because we're looking at bases. But as you recall, chloride is the conjugate base of a strong acid. It's too weak to be basic. And so even though, yes, that is technically a base, we never consider it as a base. We consider it as neutral. Same thing with bromide. Bromide, we have hydrobromic acid. Iodide, we have hydroiodic acid. And so these are all kind of neutral. However, fluoride is a base. Fluoride is the conjugate base of a weak acid, and so it's moderate in strength. And so this should be the one that's most influenced, because here, if we have PbF2 solid going to Pb2 plus fluoride, in this case, H plus can take that out, 2 fluorides. So if we have 2 H pluses, it can make 2 HFs. So that, if we want to do it quantitatively, we do KSPA. So this one would be most soluble. The KSP equation for FES, so yeah, right. This is the KSP, asterisk or double dagger, I called it. This is the one in the book that is correct, true. That is a correct KSP equation. You can go back to the notes and we talked about that one in depth. 13. Insoluble substances have solubilities of 0.1 molar, less than 0.1. This is just kind of a gray area. 10 to the minus 1.1 molar. That's kind of an arbitrary cutoff. Some books may have it, a different cutoff here. But the water solubility charts use this quantitatively. Activities are typically larger than stoichiometric concentrations. That's false. Activities are typically smaller. In other words, the effective concentration is usually smaller. We'll talk about this when we get to the lab. I'm supposed to do the lab before this. But anyway, the effective concentration, you could go back to chapter 14, which talks about clustering and pairing, that type of stuff. 15 is this one page of that in chapter 14. Number 15, which is expected to deviate most from ideal behavior? This is also from chapter 14. I would expect, well, this is aluminum 3 plus here, and this is going to be calcium 2 plus, and this is sodium plus. So this one will deviate the most. Because this one will have, with a 3 plus, it will have more tendency for clustering of chloride ions. The chloride ions don't completely break free from here. And we get clustering and we get ion pair formation, which is like this, where the chloride pairs with the aluminum and we have an AlCl2 plus pair. These pairs can be broken apart. We get clustering and pairing. And it's going to be more of a problem at higher charge. The more the charge, less they deviate. And again, this is chapter 14. Silver chloride is more soluble in all right. This is common ion effect. This decreases solubility. And this is common ion effect that decreases solubility. And so it's water versus sodium nitrate. And actually, did I repeat this? This is the same question as earlier. I think. To be more soluble in water, sodium chloride, and sodium nitrate. This is one additional. This is the exact same question as earlier. It's the uncommon ion effect. So it wasn't supposed to be a repeat. It should have been something different. All right, 17. What is the solubility of aluminum hydroxide at an equilibrium pH 4.2? And so this one we could do here. Try to squeeze it in here. I'll squeeze in. Actually, let me go to. Oops. I want to do. Okay. For some reason, this didn't quite work out. Here. Anyway, that bonus is not. The bonus I included already. Here, the solubility. This is just aluminum hydroxide. Solid going to Al3 plus 3 hydroxide. We have an equilibrium, so it doesn't matter whether initial change. We want the equilibrium. So the equilibrium is a pH of 4.2, which is a pOH of 9.8, which is a hydroxide concentration at equilibrium of 10 to the minus 9.8. Let's do that. 1.58 times 10 to the minus 4. So I have an equilibrium of 1.58 times 10 to the minus 4 here. And then I have this one. This is what I'm solving for. So I just need the KSP. The KSP we got earlier. So 10 to the minus 33. So let me see what KSP is. Yeah, 1.3 times 10 to the minus 33. And this is going to equal the aluminum concentration. Aluminum concentration is going to be our solubility. So we're going to assume that this was 0 here. The hydroxide could be anything. We don't know what that was. But the aluminum was 0 because initially no aluminum hydroxide is dissolved. We might have had hydroxide in there to begin with. And so this is going to be plus S. So this is going to be the aluminum concentration and times the hydroxide concentration cubed. So I'm going to take my hydroxide ion concentration, cube it, and then I'm going to get my KSP 1.3 times 10 minus 33. So invert this, and then times 1.3 times 10 to the minus 33. That should give me my aluminum concentration, or the solubility. 3.2 times 10 to the minus 4. More. 3.2 times 10 to the minus 4. More. Do I see that? This is 330 micromolar. 330 micromolar, that would be 330 times 10 to the minus 6 molar here. And so this would be if I go 10 to the minus 6 here, this would be 320 micromolar. Then move the decimal 1 or 2 over. That gives me 10 to the minus 6. So that would be 320 versus 330. So it's off a bit. So let me double check my calculation here. So pH of 4.2. Give me a pH of 9.8. And then that gives me a, oops, I just screwed it. Make sure negative 9.8, 1.58. Maybe it's just a round off error because I'm carrying all the digits in my calculator here, and so I have 1.584, etc. times 10 to the minus 4, and then I'll cube that. One divided by 3. Round off error in the answer key, I'm saying 5.41, and then I'll invert that times 1.3 times 10 to the minus 33. Oh, I must have made some kind of calculation error, maybe. Now I get 2.40 times 10 to the minus 30. 2.40 times 10 to the minus 30 molar. Well, 10 to the minus 30 is not nano, that's for sure. And it's none of these here. Did I screw up my calculation? So let me try it one more time here. Shift to the negative pOH (1.58 times 10 to the minus 10). Oh, I did it. Times 10 to the minus 10. Yeah, that seems right. I mean, if the pOH is 9.8, I think I screwed it up here. This can't be right. It's closer to minus 10 than that. And so I did make an error here. 1.58 times 10 to the minus 10, and then we'll cube that. 3.98 times 10, and invert that, times 1.3 times 10 to the 33. That should give me my aluminum or solubility. So 10 to the negative 33. Okay. one more time. We should have 10 to the minus 9.8. Cubed. It gives me 10 to the negative 30 invert times 1.3 times 10 to the negative 33. Yeah. So I get the same answer. Actually, no, I don't. 3.265. 3.265 times 10 to the minus 4. I didn't care enough digits. 3.265 times 10 to the minus 4, which is going to be 326.5 times 10 to the minus 6. So this is at 330. That's a 2 sig figs. A micromole. All right. Took some time to do that, but you can fast forward. All right. 18. If 5 liters of blood to 4 sig figs, we're going to assume 1.30 times 10 minus molar free iron 2. So iron 2, there's iron 2 in blood, and a lot of the blood is complexed in hemoglobin, and so this is the free concentration. It's mixed with 2 milliliters of 6.0 molar sodium cyanide. What percentage of the free iron 2 plus remains? We've got to assume that the hemoglobin free iron equilibrium is not shifted. Otherwise, it's a simultaneous problem. And so we'll just say it's a fixed. So we're going to assume it's this amount of fixed free iron. All right, so what's going to happen is iron 2 plus is going to be attacked by the cyanide. And how many cyanides attack it? Well, I don't know. I mean, once you start looking at the charts, once you start looking at the chart, then you'll know it's 6. And looking at the chart, you don't have to memorize these things. You can just look it up here. It's okay. Look it up. Yeah. Iron is coordination number 6. Now, the tricky thing is this iron 2 or iron 3? And so if you look at the first one, EDTA is a 4 minus, so this is iron 2. So this is going to be the complex with iron 2, which is 2.1. We don't want EDTA, we want cyanide. Cyanide is 1 minus. We have 6 of them. That's minus 6. So iron has got to be plus 2. That's 10 to the 37. And so we need 6 cyanide. Then we're going to form this. Actually, I'm not going to use brackets for this. Oh, here it is. I didn't have to look it up. All right. So we'll just set up an ice table here. Assume we have 1.30 times 10 minus 5 free iron. 1.30 times 10 minus 5 here initially. And then 2 milliliters of 6 molar. Oh, we'll have to do a solution here. So actually, I can't use this as is. Let me erase this. So we'll have to do a step by. Whenever we mix 2 solutions together, we'll have to do that. And so let's calculate the new iron concentration. Okay, free can also be in this context. So this is complex iron here, the cyanide one. And also there's hemoglobin in blood. which is another complex of iron. And so we have iron 2 plus concentration is going to equal, it's 5 liters, so that's 5,000 milliliters. So this is going to be a 5,000. Now the combined volume is going to be 5,000 plus 2 milliliters, so that's 5,002. So it's a 5,000 to 5,002 dilution of 1.30 times 10 to the minus 5 molar. This is a pretty marginal dilution, but since we're doing it, we'll go ahead and calculate it. Times 1.3 times 10 to the minus 5. 1.2994. 1.2994 times 10 to the minus 5 molar. However, for the cyanide, it's going to be more significant. Sodium cyanide is a strong electrolyte. Sodium is just going to be a spectator. So the cyanide is going to be a 2 to 5,002 dilution, 6.0 molar. And so 2 divided by 2,002 are 5,002 times 6. And we have a concentration of 2.399 times 10 to the minus 3 molar. And so this is 2.399 times 10 to the minus 3 molar. And the cyanide is going to be 1. Oops, that's not right. What's that? This one, the cyanide is going to be 2.399 times 10 to the minus 3 molar. The iron 2 plus is going to be 1.2994 times 10 to the minus 5 molar. Okay. The complex iron here is going to be 0, actually. But if we look at this K, it's huge, and so we need to reset this. So what I'm going to do is, I'm not going to go this way. I'm going to just reset the initial conditions. So the reset is, we'll get rid of the limiting reagent here. And so this is going to go to 0 molar. So this is minus this. Yeah. Because of the stoichiometric ratios here, this is going to be minus 6 times the limiting reagent. So I'm going to go 6 times 1.2994, 6 times 1.2994 times 10 to the minus 5. That gives me 7.7964. So this is minus 7.7964 times 10 to the minus 5. And so my new initial conditions, let's go ahead and do that. Bring this down here. Look at this extra line here. So my new initial conditions will be minus 2. This is going to be 2.321 times 10 to the minus 3. And this is going to be plus the limiting reagent here. It's a 1 to 1 to 1. I mean 1 to 6 to 1 ratio. So this is going to be 1 to 1. And so that's just going to be 1.2994 times 10 to the minus 5. Okay, now we'll go ahead and proceed. And so the change is going to be plus x. This is not s, by the way. X plus 6x here minus x. And so at equilibrium, we're going to have x molar here, 2.321 times 10 minus 3 plus 6x molar, and 1.2994 times 10 minus 5 minus x molar. Yeah. All right, the Kf is going to equal the concentration of the products over the concentration of the reactant. So this is why I didn't use a square bracket here. So I can use a square bracket right here to indicate the molar concentration of this here. Let's raise to the first power. And then we're going to have iron 2 plus here raised to the first power. And then we're going to have cyanide here raised to the 6th power here. Let's plug everything in here. This is going to be 1.2994 times 10 to the minus 5 minus x divided by x times 2.321 times 10 to the minus 3 to the minus 3 plus 6x. The whole reason for resetting it is so that the simplifying assumption would work. The simplifying assumption should work here. It's heavily favored the product, so I don't expect much of the reverse reaction to occur. And so the simplifying assumption is going to be x is going to be a lot smaller than 10 to the minus 5, and 6x is going to be a lot smaller than 10 to the minus 3. So which one is bigger? Change x. And so we'll just say x is much smaller than 10 to the minus 5, which means 6x for sure is going to be a lot smaller than 10 to the minus 3. So this is going to give us 1.2994 times 10 to the minus 5 over x times 2.321 times 10 to the minus 3. Okay, this term has to be raised to the 6th power because cyanide's to the 6th, so I don't want to forget that. This is raised to the 6th power here. Okay, now I can solve for x. So I'm going to do 1.29994 times 10 to the minus 5, 1.2994 times 10 to the minus 5, divided by 2.321 times 10 to the minus 3. Then I want to raise that to the 6th power. Okay, divided by 10 to the 37. 1 times 10 to the 37. And I get 8.31. X equals 8.31 times 10 to the minus 27. Okay, let me just make sure I did it correctly again. So I'm going to just redo the calculation. In this case, I'll do just do 2.321 times 10 to the minus 3. 6 power times Kf. And then invert that times 1.2994 times 10 to the minus 5. 8.31 times 10 to the minus 27. Okay, then we have to justify this. And so we pick the bigger percent change. The bigger percent change will be in the numerator. And so the bigger percent change will be 10 to the minus 27. The bigger percent change is because look at the initial. Even though this is a 6x, the initial is 10 to the minus 5 versus 10 to the minus 3. 10 to the minus 5 is much smaller than 10 to the minus 3 times up 10 squared. So this would be 10 to the minus 27 over 10 to the minus 5. This is 10 to the minus 32, 10 to the minus 30. So 10 to the minus 30%, which is valid. And so what we're going to have here is this is going to be 8.31 times 10 to the minus 27. This is going to be about, the change is so small, 10 to the minus 27 out here. Even though I multiply by 6, it's still going to be of that order of magnitude. So this is going to be about 2.321 times 10 to the minus 3. And this we saw is such a minor percent change. It's going to be about 1.2994 times 10 to the minus 5. So these are my equilibrium concentrations. And then I'm going to do a K check for these. I'm not solving, oops. So let's do a K check here. So it's going to be 1.2994 times 10 to the minus 5 divided by, divided by 8.31 times 10 to the minus 27 divided by 2.321 times 10 to the minus 3 to the 6th power. Yeah, and the K check works out 1.0002 times 10 to the 37. That works out. All right, and then the question is, what is the percent free iron that remains? And so the percent free iron that remains is we take a look at the amount remaining here. Over the initial. So this is the amount remaining here, but the initial is our original initial way up here, not our reset initial. So to do this calculation, let's see, percent remaining is equal to 8.31 times 10 to the minus 27. That remains over our initial of 1.2994 times 10 to the minus 5. That's how much we started off with initially times 100%. That's how much we started the reaction mixture with. And so 8.31 times 10 to the negative 27 divided by 1.2994 times 10 to the minus 5 times 100. And we get 6.39 times 10 to the minus 20%. I think we're only allowed 2 sig figs here. Or actually no sig figs. Yeah. It's about 10 to the minus 20%. This has no sig figs. About 10 to the minus 20% remains. And then this wasn't asked, but we could do this calculation. What that means is 100% minus 10 to the minus 20% equals the percent iron 2 plus complex. Which is going to be like 99.99. We need like the 29s here. Something like that, percent complex. Rounding that would be 100%, but it's not really 100%. A little bit remains, but that's so little. I mean, we could calculate how much. Just save this. Post this as well. Okay, calculate the milliliters of 6.0 molar ammonia required to dissolve 2.5 grams of silver chloride. So the first step for this one is we need to determine the solubility of silver chloride in 6 molar ammonia. The solubility in water would be KSP. This is going to be solubility in ammonia, which is going to be a KSPF. So the KSPF problem here. So first off, we need to get the KSPF equation. So it's silver chloride going to silver ions and chlorides. This is we have KSP. The KSP for silver chloride, I think we used earlier, but I'll just look it up in our chart here. 1.8 times 10 to the minus 10. And then what we're going to do is we're going to combine that with the KF. So for ammonia and silver, how many ammonias attach? So you might know this already. It's 2. But if not, we just look it up here. It's 2 ammonias. It's the diamine. 1.6 times 10 to the 7. And so this is a perfect candidate for, a good candidate for the combined method, because the first step is small, the second step is large, and therefore the silver ion concentration should be fairly negligible. And that's what we need. Because the equilibrium, the silver ions are going to cancel out with combined. It's going to give us 2 ammonias. All the silver ends up in the complex. It's usually a pretty good assumption, because over here, all the iron in the problem above pretty much ended up in the complex. I mean, if we were to round that, it's 100% complexed here. Very little free iron remains. The same thing here, very little free silver ion remains. We end up in the complex. So we end up with KSPF. It's going to be KSP times KF. And so 1.8 times 10 to the minus 10 times 1.6 times 10 to the positive 7. 2.88 times 10 to the minus 3. So I'm just going to write this in decimal form. 2.88 times 10 to the minus 3. Since you could do it either way. It's kind of small, a little bit small. So it'll favor the, we want it big to favor this, but maybe it just favors enough. So this is 6 molar ammonia, and so we're seeing what is the solubility in 6 molar ammonia. So let's assume nothing is dissolved yet here. And then this is going to be minus 2s. This is going to be plus s. This is going to be plus s molar. And so we're going to get 6.0 minus 2s molar here. This is going to give us s molar here, s molar here. I'm not going to reset this. Just look at the K value for this. Just leave it as is. And so this is going to equal the complex concentration, which is S, times the chloride concentration, which is S, divided by the ammonia concentration, which is 6.0 minus 2S squared. We have the 2 here. And so what is this going to go to? So this is going to be S squared over, I'm not going to use a simplifying assumption here, although maybe I could. We'll just try. We'll try the SA. Since the cost of trying, it's not, oh shoot, I'm going to get rid of that. Get rid of this. So just go ahead and try the simplifying assumption, see if it works. I mean, it's favored to reactant, so it shouldn't form too much product. And so if this works, then it saves me quadratic. We could do that. And so this is going to give me an S of 36 times point times and then square root that. 0.321. And then the percent change would be 2 times that. It would be 2s divided by 6 times 100. So times 2 divided by 6 times 100. 10.7%. Oh, it was actually pretty close, but it's too big. This is greater than 5%. So I'm going to have to do this quadratic. So the essay failed for this. So let's go ahead and get this in quadratic form. So this is going to equal s squared divided by 4s squared minus 12 minus 12 minus 24s plus 36. Okay. And now I'm going to multiply both sides by this here. And so I'm going to get 0.00288 times 4. And that's going to give me 0.01152 s squared minus 24 times 0.00288. The 0.06912. Then 36 times 0.00288. 10,368. 0.10368 is equal to s squared. Let me double check my first calculation. 4 times 0.00280. Yeah, that's right. Then what I'm going to do is I'm going to subtract this from both sides. And so I'll have 1s squared minus 0.01152. So 1 minus 0.01152. So 0.98848 s squared. And then plus 0.06912 minus this is x, I forget the s there, minus 0.10368 is equal to 0. All right, I'm going to use my calculator to solve this. So I'm just going to go, I'm going to go to mode on my calculator, equation, and then I'm going to choose the quadratic equation, which is option 3 for me. And then A, I'm going to plug in 0.98848. Okay. And then for B, did I get that right? Do 0.06912. And then for C, I'm going to plug in negative 0.10368. And have it solve it, and I get an X1 of 0.2907 molar. Not X, S1. My S2 value is negative 0.360 molar. It can't be negative. So 0.2907 molar. So that's the solubility. I mean, we use the solubility as a conversion factor. And what the solubility tells us is that 0.2907 moles will dissolve per liter of solution. Moles of are actually moles of silver chloride, because the way this works is that for every one of these I have, one of these had to dissolve. And so it's a 1-to-1 mole ratio. So if I have 0.2907 molar silver complex, it's got to be 0.2907 moles of silver chloride dissolved. It's a 1-to-1 mole ratio. So that comes from 1-to-1, 1 mole of the complex, because there's no other source of complex. If there are multiple sources of complex, then this wouldn't work. So for example, if there's a second reaction here that also forms a complex, then I have two sources. But I only have one source of the complex that comes from the silver chloride. So that tells me that. But before I get too far, we should do a K check for this. And so I'm going to calculate the equilibrium concentrations here. So this is 6 minus 2s. So this is going to be 6 minus, go back to my computation mode, 6 minus 2s, which is 2 times 0.2907. And that gives me 5.4186. 5.4186 more. And then my S is 0.2907 and 0.2907 molar. So we'll do a K check here, and that's I'm going to invert what I just calculated here, times 0.2907 squared. And what do I get here? Oops. Divided by 5.4186. And my K checks out. It's 0.02878. So that's good. That's 288 there. You should do a K check here. Remember, you got to square the ammonia. So the ammonia is 2 in your K check. So now what we have is calculate 2.5 grams. I don't know how many moles that is. And so we're just going to use dimensional analysis for this. We have 2.5 grams of silver chloride. And the molar mass of silver chloride we have to get off the periodic table. So get that for you here. I'll bring up the periodic table. So silver is 107.9, chloride's 35.45. Actually, I need 2 decimal places for this. I don't know why. This one did that. I like my molar masses to do 2 decimal places. This is a Chem 4 periodic table. Let's just get another periodic table here. Just use it. It's all right. We don't have to be that precise. So 107.9 plus 35.45. 143.44. 143.44 with this periodic table. Yours could be a little different because most periodic tables will do silver to 2 decimal places. Let's do this again. No. So I have the molar solubility here. And so this is going to be a liter. per 0.2907 moles. All that solution is coming from the 6 molar. So what are they asking for here? Milliliters? Milliliters. Liter of solution. So 2.5 divided by 143.44 is 0.0174 moles. So this is going to be way less than a liter. Divided by 0.2907 moles times 1,000. 59.95 milliliters. So about 60 milliliters. Let's see how many gigs. Yeah, 60 milliliters. Should do it. I double check that calculation. You double check it. You wish to separate 0.25 molar iodide and 0.15 molar chloride. Did I put a bonus? I didn't put a bonus in this one, did I? I think I forgot it. Using silver ion, does it work? In order for it to work, we need 99.9% precipitation. So the criteria here is 99.9% precipitation of one before the other precipitates. Of one before the other begins to precipitate. Other begins to precipitate. That's the criteria, whether it works or not. And so we need to calculate what percent precipitation we have. And so this is a fractional precipitation. In fractional precipitation, we just always do it the same. First, we calculate the silver ion required for precipitation. For A, to precipitate the iodide. All right, the silver ion that's required to precipitate the iodide is we just need to saturate it. That is, we need to get QSP equal to KSP. So KSP for this, for both of these, is fairly simple. We have silver iodide. Going to go to silver ions and iodide. It's just 1 to 1. So this is just silver ion times the iodide concentration here. And the iodide and the chloride are different concentrations. And so what we need to do is we need to calculate the silver ion required to saturate the solution. The silver ion required to saturate the solution is going to be KSP over the iodide concentration. And so we'll need the KSP value for silver iodide. Silver iodide is 8.5 times 10 to the minus 17. 8.5 times 10 to the minus 17 divided by the iodide concentration of 0.25. And so 8.5 times 10 to the minus 17 divided by 0.25. 3.4 times 10 to the minus 16 molar. So that's enough to saturate it. What I need to do is, if I exceed this amount, then I have precipitation. If I exceed it. Okay, B for the bromine. We have silver bromine. So this is going to go. This one splits up the same, so we could just look at the KSP to see which one's going to precipitate first. But anyway, we get the KSP. It's going to these silver ions times the bromide ions here, and then we calculate the silver ion required for precipitation, which is going to be KSP divided by the bromide concentration. And so we take a look at KSP first. For silver bromide, the KSP is 5.0 times 10 to the negative 13. And the bromide concentration is different here. It's only I do chloride. Shoot, what am I thinking? Bromide. Sorry, folks. I'm not going to edit this video. You can jump it or just fast forward if you want to skip my correction here. Okay, let's fix this. I don't know why I was thinking bromide. It's going to give you silver and chloride. Okay, so silver chloride is 1.8 times 10 to the minus, what was it, 11? Silver chloride is 1.8 times 10 to the minus 10. And then the chloride is 0.15. 1.8 times 10 to the minus 10 divided by 0.15. 1.2 times 10 to the minus 9. Greater than this concentration of silver ion will result in precipitation. So the smaller amount is the one that's going to precipitate first. One of the big mistakes in fractional precipitation is to calculate the solubility. We don't want to calculate the solubility here. We want to go straight to this. This is calculation number 1. So don't bother calculating the solubility with the common ions here, because it's useful in knowing which one is less soluble. The one that's less soluble will precipitate first, but this is more effective here. And so this only requires 10 to the minus 16 molar. This requires a lot less silver ion, so this one precipitates first. We have to increase the silver ion concentration all the way to 10 to the minus 9. So we have to go from 10 to the minus 16 to 10 to the minus 9 before chloride begins to precipitate. And so what you have to do is you have to be very careful. If you dump in too much chloride, both will precipitate. And so what we do here is we have chloride and iodide in solution, and then what you're going to do is just slowly increase the silver ion concentration. When we hit the silver ion concentration of 3.4 times 10 to the minus 16, 3.4 times 10 to the minus 16 molar silver, then silver iodide is ready to precipitate. However, silver chloride is not. So just the silver iodide is saturated. And so, and this would be saturated in silver iodide, unsaturated in silver chloride. The silver chloride is not, the concentration is still too small to equal KSP. And so then as we increase the silver ion concentration, slowly the iodide begins to precipitate. And so silver iodide, AgI, begins to precipitate. And so there'll still be an iodide in solution, because to precipitate out 100% of it, we need an infinite amount of silver ion, which we aren't going to have. And then the chloride's still going to be the same. So what's going to happen here is as the silver ion concentration increases, the iodide concentration must decrease. Okay. That's in order to maintain KSP. So if we go back up here, if we increase the silver ion concentration, the iodide concentration is going to decrease. nothing's going to happen to the chlorine concentration because it still hasn't begun to precipitate. And then we need a stopping point. We need to stop at 1.2 times 10 minus 9 molar silver ion concentration. Because if we exceed this, because if exceeded, then silver chloride precipitates. And so what we have is two precipitates. We don't want two precipitates. We just want one precipitate. But the question comes up is, okay, this is the next calculation. The next calculation is, what should we call 2 here? How much silver precipitated, silver iodide precipitated, in order to figure that out, we need to determine how much iodide remains in solution. We aren't going to get 100% because to get 100% of it, we need an infinite amount of silver. So how much iodide remains at this point? Well, we know the silver ion concentration, so all we have to do is calculate the iodide concentration. The iodide concentration remaining at this point is equal to the KSP of iodide divided by the silver ion concentration. The silver ion concentration at this point is going to be 1.2 times 10 to the minus 9 molar. And so we have the KSP of iodide, which is 8.5 times 10 to the minus 17. So 8.5 times 10 to the minus 17 divided by 1.2 times 10 to the minus 9. That gives me an iodide of 7.08 times 10 to the minus 8 molar iodide. So we didn't get 100%. So the next calculation we're going to do is what percent of iodide remains. And so we're going to calculate percent iodide remaining unprecipitated. And we can't precipitate this because then we'll start precipitating both, which we don't want to do. So percent iodide remaining unprecipitated. That's going to equal the amount that remains, 7.08 times 10 to the minus 8, divided by the initial. The initial iodide was 0.25? 0.25, yeah. Times 10 squared percent. So divided by 0.25 times 100. 2.83 times 10 to the minus 5%. That's how much iodide remains unprecipitated, and 100% of the chloride remains unprecipitated. 4. Let's calculate the percent precipitation. Percent precipitation is going to be equal to 100% minus the percent remaining. Because whatever doesn't remain was precipitated. And so I'll just do that here. And I get 99.9999%. This next digit is a 7. This is greater than 99.9% before chloride precipitates. So does it work? Yes. So the answer is yes. We get complete. Complete is just not really complete. Complete is 99.9%. Complete precipitation of iodide. Before any chloride precipitates. We leave the chloride in the solution, so we can separate the iodide from the chloride this way. There will be some residual, small amount of iodide left unprecipitated, but at least the silver iodide will be pure. So when we hit this point over here, we're going to get silver iodide here, And up here, all the chloride will be in solution, and a tiny, tiny bit of iodide will be in there. A tiny, tiny bit will be 10 to the minus 5% remaining. But the silver iodide will be pure, no chloride, silver chloride there. Okay, that's it. So good luck tomorrow on the test. And if you have questions on this, post it on the discussion link on Canvas. Okay. Have a good day. Bye.